Chapter 1, the structure and stability of atoms. An atom is the simplest particle of matter which still retains its chemical properties. So you cannot break an atom down any further and expect it to still behave the same way. Elements only consist of one type of atom. Therefore, every element is different from each other because they have different types of atoms. 118 elements have been identified. 82 elements occur naturally on Earth. 36 elements have been created, generally using particle accelerators. And elements are always abbreviated by their symbols. When we have a two-letter symbol for an element, we always have to make sure that the first letter is capitalized and the second letter is not. And we have to make sure we know the correct abbreviation for an element. For example, fluorine is the capital letter F, not the capital letter F, lowercase l. FL is for Florida, which is completely different. Here we have a modern periodic table of elements. The modern periodic table was developed by Dmitri Mendeleev. He decided or discovered that it was better to organize the elements in terms of increasing atomic number, whereas the periodic table before was organized in a way that elements were increasing in their mass. And this was a problem because, for example, tellurium and iodine. Tellurium actually has a larger mass than iodine. However, it behaves similarly to the elements in group 6. So he predicted that iodine should actually go here, and that was a correct prediction. He also suggested that there were holes in the periodic table of elements that hadn't been discovered yet, because this table was developed back in 1869. So he had what he called an Eka silicon element that was not yet in existence, or they hadn't discovered here between silicon and tin. And later on, germanium was discovered. So his prediction of organizing the elements in this manner was a correct prediction. So we have different things that we can identify on the periodic table, and I'm going to go through each of these individually, but I'm going to go back a slide and talk about the periodic table. So first of all, why is it called the periodic table? Well, we have periods, which are simply the rows here in our table, and things change periodically. So we get to the end of one row, and we see then that sodium has the same characteristics of lithium. We also have what we call groups or families in the periodic table, which are simply the columns that we see. So vertical columns are families or groups, and our rows are called periods. We can further look at the periodic table and classify our elements into metals, metalloids, or semimetals, and nonmetals. So most of the elements are metals, which means they're shiny and they conduct electricity and heat very well. They're also malleable and ductile, which malleable means you can pound out the metal into a thin sheet. Ductile means that you can string it out into a wire. Our nonmetals over here do not conduct electricity well, nor conduct heat well. They also tend to be gases at room temperature, versus almost all of our metals are solids, the exception being mercury. We do have a couple solids, carbon, phosphorus, sulfur, and iodine for our nonmetals, and bromine happens to be a liquid. In between our nonmetals and our metals, we have a group here called the metalloids or semimetals, and this is because they have properties of both the metals and the nonmetals. Silicon is a semiconductor, so it does not conduct electricity very well, but it can be doped to conduct electricity better. We can also look at what we call our main group elements, which have the letter A at the top. So we have 1A all the way through 8A, ignoring these elements here. These elements are called transition metals, or our transition elements, because they can transition between oxidation states. Down here we have our inner transition metals, and most of these are radioactive. We also have special names for some of our groups. Group 1 is known as the alkali metals. These are very reactive with water and are not found alone in nature. Group 2 is known as the alkaline earth metals. Both alkali metals and alkaline earth metals, when they react with water, they form bases, which is why they are alkaline. If we move over to this side of the periodic table, group 7 is known as the halogens. These are also not found alone in nature. And group 8 is known as the noble gases. These were also called the inert gases because it was once thought that they did not react with any other element. However, argon, krypton, and xenon have been shown to react with some halogens, especially fluorine. So what is chemistry? Chemistry is the study of matter and the changes that that matter can undergo. So what is matter? Well, matter is anything that has both mass and volume. And we looked at these terms in the last chapter. Recall, mass is simply the amount of substance that exists in that object, and volume is the amount of space that that object takes up. So we have to have some amount of substance and take up some amount of space. Therefore, everything around us is matter, whether it's water, we have a big chunk of gold, that would be nice, or a bowl of sugar, the air that we breathe, it is all matter. So looking at some of the properties of matter, first we'll study physical properties. These properties are observable properties which will not change the composition of the matter. So a physical property is something that you can observe with your 5 senses, or something that you can measure, like the length, the volume, the mass, what color is the element, does it smell? These are all physical properties. So you're making a physical observation. A physical change is something where we change the matter from one state to another, but do not change the composition. And what I mean by that is we can take water and heat it until it boils. So we're changing the liquid water into gaseous water, but water is still water. It's still H2O. We did not change the composition. So any change from solids to liquids, liquids to gases, gases to solids, etc., those are all physical changes. A physical property can indicate a physical change. For example, water boils at 100 degrees Celsius. So the boiling point of water is 100 degrees Celsius. That's the physical property to show that the physical change occurs at that temperature. On the other hand, chemical properties. Chemical properties look at how can we change the composition of the matter that we have. So chemical change then looks at a transformation. We are rearranging the way that the atoms are bonded to each other. However, we are not changing the atoms themselves. So what you put in has to equal what you get out. Down here, we are burning hydrogen in the presence of oxygen. So this is a combustion reaction. Anytime we have oxygen present, it is combustion. But notice we have 4 hydrogen atoms to start and 4 hydrogen atoms to end. We have 2 oxygen atoms to start, and we have 2 oxygen atoms to end. They're just bonded in a different way. Hydrogen was only attached to itself, oxygen was only attached to itself, but now we formed new bonds between oxygen and hydrogen. So this was a chemical change. So how things react with each other, whether they react with an acid or a base, or they're flammable, these are all chemical properties because it's going to show that we can change the composition. Other types of properties we can study are extensive versus intensive. And we can look at this as quantitative versus qualitative. A quantitative means quantity. We're looking at how much of something is there, which is an extensive property. How much does this extend? What is its mass? What is its volume? These are extensive properties because it depends on how much of the substance is there. Versus an intensive property, which we're looking at the quality of it. Intensive properties do not depend on the amount of the substance that is there. For example, what color is the substance? Does it smell? Is it hard? Things like that. Is it soft to the touch? It just depends. So measuring is an extensive property. Identifying something with our 5 senses tends to be an intensive property. So now we're going to take a look, excuse me, more in depth at the atom. John Dalton formulated this hypothesis called the atomic theory. And he stated that elements are composed of atoms, and that all the atoms of a given element are identical, meaning that they have the same size and mass. Now, this part here is not true, and we'll talk about that later in what we know to be isotopes. Compounds are composed of atoms of more than one element. The ratio of the number of atoms is either an integer or a simple fraction. So things combine in a predictable way. And a chemical reaction only involves the separation, combination, or rearrangement of atoms. So we're saying that we are not creating new elements in a chemical reaction, which is true. If we're going to create a new element, we have to undergo a nuclear reaction. Studying the law of conservation of mass. Antoine Lavoisier, he was a Frenchman, and he did a test where he was studying the rust of iron. He put it in an enclosed container and took the mass before the iron rusted and after the iron rusted. And he noticed that the mass of his enclosed system did not change, even though the mass of the iron went up. So how did this happen? Well, the law of conservation of mass states that the mass that you start with has to be the mass that you end with. So we cannot create matter in any type of reaction. Conservation of mass. What you start with is what you end with. For example, sulfur plus iron gives us a compound here of iron sulfide. If we start with 32 grams of sulfur plus 56 grams of iron, we have to end up with 88 grams of product. We cannot create more. We do not lose anything in the process. We might have some sulfur left over or some iron left over if the reaction wasn't complete. But the mass stays constant. We cannot create matter in any type of reaction. Law of definite proportions. This is stating that if we have two different elements, X and Y, they will combine to form a specific compound. And within that compound, the ratio of the atoms has to remain constant. For example, if this was oxygen and this was hydrogen, we've formed a water molecule over here. And this water molecule means that we have one oxygen for every two hydrogen atoms that we have. This is the way that this has to be. We cannot have a water molecule that has anything different than two hydrogens and one oxygen. It is a specific ratio, a definite proportion. We can, however, have multiple proportions. So we can look to see how two different elements can combine in different ways. For example, carbon monoxide, we have a ratio here of one carbon atom to one oxygen atom. Here we have carbon dioxide, meaning we have one carbon atom for every two oxygen atoms. So we see that we have these ratios here, and they are proportionate to each other. Here we have double the amount of oxygens that we have here, a ratio of 2 to 1. So we will see multiple proportions exist in either whole numbers or simple fractions. So now that we talked about the atom, we're going to discuss what composes the atom. Discovering the electron. J.J. Thomson studied cathode ray tubes. And a cathode ray tube here has been evacuated of all the air, and it is hooked up to a high voltage source. So we have electricity going from the cathode to the anode, going from the negative plate to the positively charged plate. We have two choices here. We can apply a magnetic field or we can apply an electric field. And depending upon the size or the strength of these different fields, we see deflection in the way that the beam is traveling. If the beam is attracted to the force that is applied, we see that the electrons go towards it, versus if it was a negative field, we would see the electrons go away from it. If no field is applied, or if these two fields are balancing each other out, we see that the beam goes straight through. Now, altering the size of the charge, or not the size of the charge, altering the size of the magnetic field or the size of the electric field, the strength that we have there. Different results were collected, and he discovered that there was a set ratio of the charge to the mass on what he called the electron. So here we have a smaller cathode ray tubes, and these were what old school TVs used to be made of. How they used to be so huge, it was because they needed the cathode ray tubes in them. So here I have the beam of particles. I'm not applying any external field. Here I've applied a magnetic field, and I see that the particle beam is going away, which means I must have the negative end of the magnet applied, versus if I flip the magnet around, I have the positive end of the magnet, and we see that the particles are attracted to the beam. So we saw with this experiment that electrons are negatively charged, but we don't know what the charge is. So Millikan came along with his oil drop experiment, and here we have some oil, and it becomes atomized. So we have this fine mist of particles, so the tiniest particles possible. And we have a pinhole here, so the oil drops can fall through this hole. So they're traveling downward, acted only upon by gravity. Now, once the particles come down here, they are hit with an X-ray source, which just means that we're going to create some charges in this environment. And those charges are going to stick to these particles. And the particles, the bigger they are, the more charges that are going to stick. If you think of these as little tiny Velcro balls falling through this hole, the bigger the Velcro surface, the more things that could stick to it. And what we're looking at is a charge. So we charge these oil drops, and then we have two electric plates here. So we're creating an electric field. And changing the field, the strength of the field, once again, we can get this so that the positively charged plate here will attract the oil particle and suspend it. So we can counteract gravity and suspend the particle, and then measurements can be taken. And with these measurements that were taken then, and using what Thomson had discovered about the charge to mass ratio, the actual charge on the electron was discovered, and that is 1.60 times 10 to the negative 19th coulombs. So we discovered the electron, now we're going to discover the proton. And Lord Rutherford did this experiment. He did quite a few experiments. He was the first one to do nuclear transformations. It was once thought that an atom was simply a positively charged sphere that had negative electrons floating around it. So he did an experiment where he had a piece of gold foil and an alpha particle emitter. So this is an alpha particle emitter, which means is emitting positively charged particles twice the size of an electron. The prediction was that all of the particles should go through. The results, however, were that, yes, most of the particles went through, but sometimes they were deflected, and in about 1 in every 20,000 particles actually came back to the source. So the original assumption that this was what the atom looked like was incorrect. And instead, he discovered that within an atom, there is a tiny center to it where most of the mass is, and it is positively charged. He knew it was positively charged because the particles here are positively charged, and they were deflected. They did not stick, they bounced off. They were denied, right? They were, what's the word I'm looking for? Repulsed, repelled, okay? Positives repel other positive charges. So yes, we did still see some of the particles go through. Well, most of the particles went through, which means that an atom is almost entirely empty space with just a little bit of mass in the middle. So electrons, protons, and neutrons, where are they? What are their charges? Electrons, we denote as having a -1 charge, and they are found on the outside of the outside of the nucleus, thought to float around like planets orbiting around the sun. You will notice too that the mass of an electron is about 10,000 times smaller than that of protons and neutrons. So protons are located in the nucleus, and they are positively charged. So the P for proton is P for positive. Neutrons are also found in the nucleus, and they are neutral. So neutron is neutral, meaning that they have 0 charge. Notice that the proton and the neutron are almost identical in mass. So once again, nucleus only contains protons and neutrons. Outside of the nucleus, we see all of our electrons. So what can we learn about a specific atom or looking at a specific element? On our periodic table, it tells us different things. First, we can look at the atomic number. And in our periodic table, the atomic number is listed above the elemental symbol. The atomic number tells us the number of protons that an atom has. If it is a neutral atom, then it also has to have the same number of electrons, because positives and negatives have to balance out equally if the charge is going to be 0. The atomic number tells us our chemical identity. Every element has a different atomic number. So you can have the same number of electrons, you can have the same number of neutrons, but you cannot have the same number of protons if you are a different element. And the way that we can represent specific, what we call isotopes of an element, is in this designation, where X is going to be our elemental symbol. Our atomic number is going to be located down here, and then we have our mass number located up here. And our mass number tells us the total number of protons and neutrons that an atom has. So we cannot find the mass number on the periodic table. It has to be given to us. Has to be given to us because it is a whole number value. So where do these mass numbers come from? Well, we can look at the isotopes of different elements. And an isotope is simply going to vary in the number of neutrons. Has to have the same number of protons, same number of electrons, different number of neutrons. So here we have hydrogen. 1 is the mass number, 1 is the atomic number, meaning that 1 minus 1 gives us 0 number of neutrons. This is called heavy hydrogen or deuterium. Mass number has gone up by 1. Atomic number stays the same. So we see 2 minus 1 gives us our 1 neutron in the nucleus. This is called tritium. Mass number of 3, atomic number of 1, never changes. 3 minus 1 is 2, telling us that we have 2 neutrons in this nucleus. 1 proton, and it would therefore have 1 electron if this was a neutral atom. So here's a nice little block representing carbon. It's something that we would see on a periodic table. Atomic number listed at the top, which once again tells us that carbon has 6 protons. Every carbon atom has to have 6 protons. If it's neutral, it has 6 electrons. And we do not know how many neutrons a specific carbon atom has. Now, we have our atomic mass listed. And these numbers are almost always some sort of decimal. And this is because of the different isotopes that will naturally occur. Here we can look and see carbon 12. We call this carbon 12. We call this carbon 13. So we can say the element and its mass number. There's a natural abundance, 98.9% of carbon 12. The natural abundance of carbon 13 is 1.10%. So there's more carbon 12, much more carbon 12 than there is carbon 13. So what we see then in our atomic mass is what we call a weighted average. And that is because there's so much carbon 12, we see that the average atomic mass is closer to 12 than what it is to 13. For example, let's say instead this was 50% and this was 50%. What would the average atomic mass be? 12.50, because it's in the middle. If we had 99% carbon 13 and 1% carbon 12, we would see the mass be 12.99. So these are where our atomic masses come from, but no single carbon atom weighs 12.01 because we cannot have a fraction of a neutron. But when we're calculating atomic masses, or not calculating atomic masses, when we start to calculate molecular masses, we will use these atomic masses. Carbon 12 is the standard from which all other elements have been measured. And generally speaking, we will use 4 significant figures with our atomic masses. Avogadro's number. What is Avogadro's number? Well, Avogadro's number is representing 1 mole of any substance, and a mole is a counting number. So 1 mole of anything equals 6.022 times 10 to the 23rd of that substance. A mole works the same way that a dozen or a pair works. If I have a dozen of something, I have 12 of it, no matter what it is. 12 bunnies, 12 donuts, 12 pencils, I have a dozen. They're all different from each other, but the counting number is the same. Or a pair, I have a pair of shoes, I have a pair of earrings. 2, I'm always representing 2 if I say I have a pair. So a mole is just representing a much larger number because atoms are so infinitely small. This many number of atoms could fit on the tip of your pencil. Molar mass. So how does molar mass differ from atomic mass? Well, molar mass of a substance is going to be the mass of 1 mole of that substance. And the nice thing about it is, if we go back here and look, if I have 1 atom of carbon, it weighs 12.01. If I had 1 mole of carbon atoms, it would weigh 12.01 grams. So I have atomic mass units for measuring 1 atom, where I have grams to measure 1 mole of those atoms. And because I then now can put something in terms of grams per mole, I can convert in between a mass and the number of atoms that I have present. So here's the picket fence, which shows how the mass can be determined. 1.66 times 10 to the negative 24 grams is equivalent to 1 atomic mass unit. So we have a conversion factor here because I said carbon 12 is the standard from which all other atoms are measured. So, oops, sorry about that. So 1 gram is equal to 6.022 times 10 to the 23rd atomic mass units, or if we see here, that is 1 mole. So we have grams per mole. Molar mass, here is our unit, and we have conversions then to go between mass, moles, and number of atoms. How do we convert? Anytime you're going to go in between grams and moles, we have to have the molar mass. Regardless of whether we're going to divide or multiply, this is the conversion factor that we need, molar mass. Grams into moles, I'm going to divide. Moles into grams, I'm going to multiply. So just the opposite. I can also convert in between moles and the number of particles that I have, whether they be atoms, molecules, formula units, electrons, ions, whatever. Here, we have to use Na, which stands for Avogadro's number, 6.022 times 10 to the 23rd. If I'm going from moles into a number of atoms, I'm going to end up with a really large number over here because I'm multiplying by Avogadro's number. Here, I start with a really, really large number, divide by Avogadro's number, and end up with a much smaller number. So we have to make sure that these things make sense. We can have grams, we can have a kilogram of something, and therefore have maybe 55 moles of it, which then means that we're going to have 3 times 10 to the 24th or 25th number of particles in that number of moles, okay? I will never have 3.0 times 10 to the 25th moles of something. That number does not make sense. So make sure that when you're doing these conversions, you're paying attention to the units always and thinking about, does my answer make sense in the magnitude of it? Last bit of this chapter deals with radioactivity. So we're going to go back to Rutherford here, and he studied and discovered the different types of radioactivity. So we have a radioactive substance here, say plutonium. In this lead block, it's surrounded by lead to absorb some of that radioactive stuff coming off. Goes through a plate. Once again, we have electrically charged field here, and different particles were deflected in different ways. First thing, we can look at the alpha particle. Notice there's not much of a deflection, which means that it is heavier than the beta rays. We also noticed that it was going down, i.e. it was attracted to the negative plate, so it must be positively charged. Gamma rays go straight through, meaning they have no charge, so they are not affected by any type of electrical field. These are high energy waves, very, very short frequency. The last particle here is what is called a beta ray, and this we see is deflected much larger because it is much smaller, and we see it is attracted to the positively charged plate. Therefore, the beta ray must be negatively charged itself. So looking further at the different types of radioactive decay, alpha production. When an alpha ray is given off, it is simply a helium nucleus. So it has a mass number of 4, an atomic number of 2, but it has no electrons. So it is charged with a positive 2. So it has a significant mass in terms of the radioactivity of it. Now, alpha rays can simply be deflected or stopped by a sheet of paper or your skin. However, they can be harmful if they are ingested or breathed in. Beta production. A beta ray is simply an electron. So notice no mass number because it has no neutrons or protons. And we have a charge here for what is called the atomic number, right? So that shows us that it's an electron because it is a negatively charged particle here. I'd like for you to pay attention to the fact that we have to have a balanced equation here, which means that the top numbers have to equal each other. 238, arrow sign, we can think of that as an equal sign, has to equal 4 plus 234. On the bottom, 92 equals 2 plus 90. Same thing down here, 234 equals 234, so this has to be a 0. 90 equals 91. Well, that wouldn't make sense unless I subtracted 1 from it, meaning that an electron was emitted, because 91 minus 1 gives us 90. Beta rays are slightly more harmful because they are electrons, so they can penetrate much further. Generally, glass or sheets of aluminum will stop beta rays. Gamma. Gamma is a pure energy. So this is the stuff that comes off of a nuclear bomb, which just destroys things. Notice no mass number, no number of protons. It is simply energy. They still have to add up. 238 equals 4 plus 234. 92 equals 2 plus 90. So oftentimes in a balanced equation, we don't necessarily see the gamma rays because they are not affecting the overall mass change. We can also study positron production, which, if we look here, is just opposite in charge of an electron. So 22 equals 0 plus 22, and then 11 equals 1 plus 10. So a positive electron is what we call, or a positron is what we call a positive electron. Notice in all of these radioactive decays, we are starting with one element and ending with different elements. So we are actually changing the elements. These are not chemical reactions. These are nuclear reactions because we're changing the number of protons or neutrons in the atom itself. So here I'm starting with sodium, but I'm ending with neon. We also can have an atom undergo electron capture. This happens most often in really, really large atoms where the nucleus will actually attract an electron that is orbiting extremely close and suck it into the nucleus. So we see this change, 201 plus 0 equals 201 plus 0. And then we're losing this electron, or we're taking it in. So we're basically changing a proton to a neutron. So we see that the atomic number goes down by 1. 80 minus 1 equals 79. So nuclear reactions versus chemical reactions. We get a ton, like times 10 to the 20th more energy from a nuclear reaction than we do a chemical reaction. So lots of energy is given off here. However, there is a lot of waste that we have to deal with, whereas chemical reactions, the waste is not so bad. This waste can cause DNA changes, cellular changes, right? Cancer, things like that come from nuclear radioactive decay. Different isotopes. So we're starting with a particular element and we are changing it into another element. So we can have different isotopes and we can study which ones are more stable. And I already discussed the amount of energy that is given off in these reactions. Down here, this is an example of a reaction where actually a neutron is ejected. So this is not a specific type of radioactive decay. It is a neutron. 27 plus 4 is 31, which equals 30 plus 1. Down at the bottom, we have 13 plus 2 equals 15 plus 0. So once again, we have to have these equations balance each other out. Top numbers add up to equal each other. The bottom numbers add up to equal each other. So notice we actually bombarded an aluminum atom with an alpha particle. And by doing that, we changed it into a phosphorus atom. We can also look at changing californium into seaborgium by ejecting 4 neutrons, right? Californium can react with oxygen and create a new element. So this is how newer elements have been created in those particle accelerators, by simply taking other atoms and slamming them into each other and seeing if they stick. So here's a list of some general rules as to look at how stable a nucleus will be and what type of decay it might undergo. So nuclides or nucleons, which is just simply looking at a specific isotope of an element. When we have 84 or more protons, they are unstable. So the bigger your atom gets, the more unstable it becomes. And this is because we have to think about the electrostatic interactions. And electrostatic just means positives and negatives interacting with each other. So in the nucleus, we only have positively charged things. We have the protons. Now, positive will repel other positive charges. But we also know that there's neutrons in the nucleus. So the neutrons kind of act as the glue or like a buffer to separate the protons. So it's kind of minimizing the amount of that repulsive force that's in the nucleus, because there is a large binding energy which will hold the atom together. But the more protons that we get, the more repulsive force that the atom feels internally in its nucleus, and the more likely it is to become very unstable and split. Light nuclides are more stable when the neutron to proton ratio is 1:1. So for elements up to, say, atomic number 20, 23, let's see here. If we look down here, we see a 1:1 ratio and we follow it pretty well. Yep, up to about 20. So number of protons is 20, which means that we're going to have an equal number of electrons. We can look at this chart and see as we get bigger, we go farther away from this 1:1 ratio, and we start to see the ratio increase. We start to get to a place where we're going to get 2:1 ratio of neutrons to protons. Here we have mercury, which actually has a 1.53:1 ratio. So we need more neutrons in the nucleus to keep it stable when we've added more protons. Also, we see that even is better than odd. So when we have even numbers of protons and neutrons, it's much more stable. And then there are special cases, which we call magic numbers, which show great stability. So when we have 2, 8, 20, 50, 82, or 126, these show a particular stability of that atom. We can also look to see, depending upon what the ratio is of protons to neutrons, we can predict whether or not we will have a beta ray production or a positron production. And remember, if we're going to produce a beta ray, that is an electron. So we're giving off something that is -1. In doing that, we're actually going to increase the ratio of protons to neutrons because there are too many neutrons. So we take away an electric charge, a negative charge of a neutron, which means that it's become positive because positive plus negatives equals 0. So when we have too many neutrons, we see an electron is given off so that we can convert a neutron into a proton. Now, if we have too many protons, what we're going to see is that we're actually going to convert a proton into a neutron by giving off that positive electron or that positron. So we're basically taking away a positive charge, allowing us to change that proton into a neutron, making it more stable. So we will practice doing conversions between mass and moles and number of atoms, and we will also practice learning how to write out and balance nuclear transformation reactions. Keep studying.